A student set up the cell shown in figure 2. So if we have a look at this, this is a little bit unique in terms that we've got copper half cell on both sides, but we'll notice that if we actually take a closer look, the concentrations are different. And so because the concentration difference, there is going to be a potential difference, a difference in ability to attract electrons. We're getting a voltage of 0.16 volts, and then it asks us to explain how the salt bridge provides a connection, electrical connection between the solutions. And we need to be clear that the salt bridge completes that circuit because it allows transfer of ions. There are ions free to move through it. So wires complete the circuit by allowing electrons to move, and the salt bridge completes the circuit by allowing ions to move through. The standard electrode potential, so standard, and that's when we're under the standard conditions of 1 mole per decimetre cubed, for copper electrode is 0.34. So calculate the left-hand electrode. So remembering that the electrode potential of a cell is the right-hand side minus the left-hand side. So the right-hand side is 0.34 minus the left-hand side, which we don't know, we've been asked to calculate, and we know that it comes to 0.16. So we do some rearrangements, and if we do that rearrangements, we get x is 0.18. Think about it on a number line. So we've got our right-hand cell at always going to be the more positive, our left-hand cell at x, and the difference between the two is 0.16. So we're subtracting 0.16 from 0.34. We're getting 0.18 volts. Both electrons contain a strip of metal, copper metal, in a solution of copper 2 plus ions. Why the left-hand electrode doesn't have that same one? It's because the concentration is not the standard concentration. So it's not 1 mole per decimetre cubed. It's a different concentration. Now we want to give the conventional representation, which means we start in the middle with the salt bridge. And then on the right hand side, we want to say highest oxidation state copper 2 plus, and then in that half cell it's being converted into copper. Copper is in a different state, so a different phase, so we have a phase boundary. The left hand half cell is the same, but it's reversed, isn't it? The copper metal is being converted to copper 2 plus. It does say include the state symbols, so let's put them on. Solid AQ, AQ solid. When the voltmeter is replaced by a bulb, so that means that the electrons actually start to flow. Remember, the high resistant voltmeter just measures that push and pull and stops the electrons flowing. The EMF of the cell decreases over time to 0 volts. So over time, it eventually comes 0 volts. Suggest how the concentration in the left-hand electrode changes when the bulb is alight, and give a reason why it decreases to 0. So the left-hand one is at a lower concentration than the right-hand one. So what we know is that in the left-hand half cell, oxidation is going to occur, and copper is going to be oxidized to copper 2 plus, so the concentration will increase. And as copper is oxidized to copper 2 plus. Why does the EMF decrease to 0? Now this is a kind of a little bit of a trick question. They're wanting you to say that chemicals get used up, but in this case we're not using them up. Copper is being oxidized to copper 2 plus, but on the right hand side copper 2 plus is being reduced to copper. And so eventually the two half cells will have the same concentration. So the 0.15 is going up and the 1 mole per decimetre cubed is going down. When they reach the same concentration, there is no potential for electrons to flow because both things are the same. So why it decreases to 0 volts is because the concentration of copper 2 plus ions in each solution becomes equal. So neither one has a greater potential to be reduced.